So this lesson is on page 12 of your unit handout. We're going to be looking today at solving exponential equations. And there are two scenarios that we're going to encounter. One of them is if everything in the equation can be written with the same base. Okay, so if you have an equation that has a base of 3 and a base of 9 and a base of 81, we can solve that equation algebraically because 9 can be written as 3 squared. 81 can be written as 3 to the 4. So when it comes to solving an equation like this one, we will be able to do it algebraically. When it comes to an equation like this one, we will be able to do it algebraically. And we'll get to the nuts and bolts of this in a second. Same as this one. There's a way to solve this algebraically. Because all of these bases, 5, 125, and the square root of 5, can be written in base 5. 125 can be written as 5 cubed. Root 5 can be written as 5 to the 1/2. There's a common base here that we'll get to. There's a common base clearly here that's 3. But we're also going to be solving exponential equations if the bases cannot be expressed using the same base. But we don't know how to do that algebraically yet. It's going to be done graphically. When we learn about logarithms in the coming lessons, then we will learn that there is an algebraic way and you're expected to know how to do it. And we're also going to go back to that exponential growth and decay formula that's on your formula sheet and look at a couple of other questions relating to it. So to begin with, this is what we call an exponential equation. 2 to the x equals 32 is called an exponential equation simply because the unknown is part of the exponent. Okay? And this equation is an equation that you can solve. I don't even know that it's solved algebraically because it's just a fact. You search your memory or your head or you use your calculator to determine the value of x that 2 would be raised to get 32. But leading up to, and the answer is 5. Just think about that for a second. You can use your calculator. Don't just blindly go 2 raised to the 5, but think about 2 times 2 times 2 times 2 times 2. Think about 2 multiplied by itself 5 times, and you're going to get 32. But if I told you, and this is overkill, we don't need to do this, but if I told you that what I want you to do, forget about the 2 to the x. I know I'm writing it down and saying forget about it, but just ignore that for a second. Can you write 32 in base 2? So if there was no equation here, let's imagine, I take back my plan here. Let's imagine I just gave you the number 32 and I said, can you write 32 in a different way? And you said, well, yeah, I can write 4 times 8. I go, yeah, okay. But is there a way to write it with a base of 2? 2 raised to some exponent. With a little bit of thought, you'd say 2 to the 5, wouldn't you? And again, this is overkill. So since 32 is 2 to the 5, this equation can be written as 2 to the x equals 2 to the 5, right? But look at what we're saying. We're saying that the left side and the right side are equal, and these bases are the same, so the exponents must be the same. I don't think you need to take this logical approach when you're solving an equation like this. And by the way, you'd never be asked to solve this equation on an exam. That's just, there's nothing to it. But that's the idea behind how we're going to solve equations that have the same base. Can I write the left and the right side using the same base? Well, there's only one way to write 3 to the 3x plus 1, and it's 3 to the 3x plus 1, which tells you that if there is a common base, it's going to be 3. So can you figure out for me in your head or on your calculator, and I hope it's in your head, what exponent we raise a base of 3 to get it to be equal to 81? 4, right? 3 times 3 is 9, 3 times 3 is 9, 9 times 9 is 81. So we can write this as 3 to the 3x plus 1 is equal to 3 to the 4. And what we are about to do is change this into a grade 6 or 7 equation. the idea here, once again, is that if these bases are the same, and the powers are the same, the power is the whole thing, then the exponents must be equal. There's only one way that 3 to a thing can be equal to 3 to an apparently different thing. It's if those two things are the same. So all we do is we say that these two are equal. Be very mindful here of the fact that we're not dividing both sides by 3. We're not performing a mathematical operation. We're just saying if the bases are the same, the exponents are the same. And that means we have 3x plus 1 equals 4, and that's child's play, isn't it? To solve that, you subtract 1 from both sides and you get 3x equals 3, and that means x is equal to 1. And as far as Math 30-1 questions go, this doesn't even rise to the level of an exam question. I don't think. If it is, you're given a free mark, I think. You can confirm that if you put x equals 1 up here, 3 times 1 plus 1 will give you 4, and 3 to the 4, in fact, gives you 81. Are you with me on this? Okay. What about something like this? Well, I guess the first strategy, and as we do more and more work with logs and exponents in this unit, you'll get more comfortable with bases that are common. Your first strategy is to say maybe 36 is the common base. Like maybe, just imagine that you don't know. Maybe 36 squared will give you 216. And you go to your calculator and you try that. And since 36 squared gives you a number bigger than 216, 36 cannot be the common base. Like imagine back here that you were just totally unthinking and you said maybe 3 squared is 81. You go to your calculator and it's not. And you go maybe, because it's too small, maybe 3 cubed is 81, and it isn't. Finally you get 3 to the 4. The opposite thing is happening here, because if you take 36 squared, you get a number bigger than 216, don't you? So 36 cannot be the common base if there's one. Can I write 36 in a different base? I mean, I could write 1 to something, or 36 to 1, but that's not what I'm talking about. How can I write 36, Faye? 6 squared. So in my mind, I'm saying, well, this 36 is 6 squared. Maybe 216 is 6 raised to something. And it happens to be cubed. And I'm not saying that for sure you have to know this, but most of you, by the time we get at the end of this unit, most of you will see 216 and go, oh, that's 6 cubed. Because it's just going to be like seeing 7 squared is 49 over and over and over again. Is that correct? Is 216 6 cubed? Okay, so the common base is 6. But let's finish our work here. This is 6 squared to the 2 minus 3x. Right? And 216 is 6 cubed, but it's raised to the x. So all of these exponent laws that you learn about in Math 9 and in Math 10, you learn them again, and in Math 20, you apply them again, are really crucial in this unit. You need to know that when you have a base raised to an exponent, this thing is called a power, raised to another exponent. It's called the power of a power, and I never really liked that terminology, but this is equal to a to the b times c. The rule is you multiply the exponents. Briefly, if I have x squared cubed, the reason it's x to the 6 is because it's x squared times x squared times x squared. That's what cubed means, which is x times x times x times x times x, x times x times x times x times x times x, which is x to the 6. This is why the rule works. And what this means is that this now becomes 6 raised to the 2 times 2 minus 3x, and this becomes 6 raised to the 3 times x. And it's at this point in time, you can of course say that these two exponents must be the same. They have to be equal to each other because the bases are equal. I guess I need to talk about this. how many of you see that when we multiply these exponents, we get this? I'm recommending to you that you don't immediately write that you write the line that's above it. Whether you decide to even write this still with the sixes or not is up to you. But the point is, I think on a written response, a marker needs to see what you're doing to get that 4 minus 6x. So I think you need this line. You need the line that has the highlighting in it. And, you know, I hope everybody sees where this is going, is that you're going to land on this equation. I know that probably everybody in the room can go from here to here. I'm asking you not to. Many of you will look at it and go, that's just so obvious what's going to happen. But that's not the point of a written response. The point of a written response is to show the logical steps that you use to solve the problem. So, you know, what I would do, I'm going to erase some stuff now. What I would do is I would write that, then I would actually write this, and by the way, this will reduce errors as well. Then I would show the next step, okay? This is what I would do. So you're going to have 4 minus 6x equals 3x. I don't think this step is strictly speaking necessary. And I hope you just appreciate what I'm getting at is, I can't guarantee how these things are marked on written response, so showing more work is maybe a better idea than showing less. Pretty easy to solve. 9x equals 4. Divide both sides by 9, you get x equals 4/9, and we're done. Any questions with that example? Okay, so it gets more difficult, obviously. It's clear that there's a common base here. Let's talk about root 5 first. Root 5 is the same as 5 to the half. You learn in Math 20 that the nth root of a radicand will be the radicand raised to the reciprocal of n. So if it was a cube root, we would raise it to the third. If it was a fifth root, we would raise it to the fifth. 125 is 5 cubed. I mean, I think there's something about this question that's kind of, it's a big neon sign flashing common base is 5, common base is 5, common base is 5. So when you look at the 125, your brain should be heading in that direction. Can I write 125 as 5 to the something? And I'll leave it to you to figure out why it's 5 cubed. Okay? So that means I can write this as 5 to the x over 5 cubed raised to the 2x plus 1. And I know you know that we're going to be multiplying the exponents, but don't just write it as 5 raised to the 3 times the 2x plus 1. Write it this way first. And then this is equal to 5 raised to the half This is equal to 5 raised to the half to the 2x plus 1. And what we don't want to start cleaning up too much at once. We want to apply the exponent laws piece at a time. So on the bottom of the left side, we can write 5 to the 3 times 2x plus 1. And here we can write 5 to the 1/2 times 2x plus 1. Are we okay with that? Okay. We're not ready yet to ignore the bases and set the exponents equal to each other. We need to get it to be 5 raised to an exponent equals 5 raised to a different, apparently different exponent. Then we can put those exponents equal. So what are we going to do on the left-hand side here? Well, if I have x to the m over x to the n, maybe I won't use x. This is b to the difference of the exponents, top exponent minus bottom exponent, right? I mean, p to the 10 over p to the 4 is p to the 6. You subtract the exponents. So now what we have is 5 to the x minus 3 times 2x plus 1 equals 5 to the 1/2 times 2x plus 1. You can start multiplying these exponents out at any stage you like once you've written them in the line that you can see right at the top of the screen. Once you've written it that way, you can start multiplying stuff out. But again, if you try to do too much at once, you're liable to make a mistake. Now I can drop the exponents, and I have the following: x minus 3 times 2x plus 1 equals 1/2 times 2x plus 1. Are we okay with that move? I would multiply both sides by 2 here. Probably even before I expanded out the other side, because I would rather not work with fractions. So what I'm going to do is multiply this side of the equation by 2, and I'm going to multiply this side of the equation by 2. When I multiply the left side by 2, I get 2x minus 6 times 2x plus 1. And on the other side, I simply get 2x plus 1. I seem to recall having this conversation, I don't know if it was with you or my Math 20s yesterday. I only multiply this 2 by the whole thing because there's a multiplication in here. It's not plus. I'm not going to go 2 times 1/2 and 2 times the 2x plus 1. And now we solve it. So we get 2x minus 12x minus 6. Don't forget this minus 6 is multiplied entirely into it, meaning the negative as well, equals 2x plus 1. So what do I do here? Well, the 2x minus the 2x is nothing. If I shuffle the 12x to the other side, it becomes positive, and I end up with, I believe, negative 7. Yep. So x is equal to negative 7/12. There are many cases in math, and you've encountered some last year, and we're going to encounter more this year, where you have what are called extraneous solutions. Do you recognize that phrase? That you do the math right and you get an answer, but the answer is incorrect. It won't work. You never have to check for extraneous solutions here. Well, never's an extreme word. You might have to if the equation is exponential in addition to another type of equation. Example 2. If I said to you, what is the solution to this equation? You don't know how to do it algebraically. I think there might be 1 or 2 people who can do it algebraically right now because you've learned about logarithms on your own. So the only way for us to solve this is graphically. I'm sorry, I apologize. Does anybody have any questions with any of the steps here? All right. So we're going to solve this graphically because we have no other choice, really. So y equals 12. I like the y1 equals y2 method. You know, your textbook, if you are interested in that, zeros the equation all the time and finds an x-intercept. I don't prefer that. Now, it's always nice to set up window settings that you think are going to be helpful. Zoom standard might work and it might not. So in my mind, since y1 is 12, I need to go up to, you know, more than 12. I don't care what you go up to. We can adjust it later, but I want to be able to see that y equals 12. Now, when I take a look at this side, y equals 2/3 raised to the x minus over 4. 2/3 is a base. I'm going back to the very first lesson in this unit. 2/3 is a base between 0 and 1. This will be a decreasing function. Okay? It will be a decreasing function that looks something like that. there's actually a b value in terms of the parameter b of 1/4. This is a y-intercept of 1. A b parameter value of 1/4 stretches this horizontally by 4. So it's just going to be this wide sloping thing that goes down. Maybe negative 10 to 10 will do it. But see, I know that I also have y equals 12. So now I'm thinking maybe negative 10 to 10 won't do it. The point of intersection is going to be way over here, someplace up in quadrant 2. You know, I can put, if you want, for my x, let's go 0 to 10 just to make a point. There's 12, and I've entered something incorrectly here. What did I enter? Oh, I got an extra bracket. There's that one, and there's the exponential one. So because of that b value of 1/4, it's really stretched it out, and the y-intercept is still only 1, so we have to look back here somewhere. And negative 10, I don't think is going to cut it. Maybe negative 25. We can always overshoot it. Oh, I didn't plan that, but you know, it's just like perfection. If we went negative 20 and we didn't see it, we would go negative 30. Anyway, it's there. We can find the solution to this equation, calculate, intersect. It's approximately negative 24.5. That's the best we can do here. So I'll put a little dot over the equal sign to mean approximately. And the next one is kind of difficult. And the reason is the base on the left is a whopping 75. This is an increasing function that is going to be incredibly steep and very close to the asymptote, very close to the origin. Like at small values of x, it's going to be very, very close to the asymptote for negative values of x. On the other hand, we have a base of 3 that's been stretched vertically by a factor of 2.5. It's hard to wrap your head around what the window setting should be. And why am I giving this one to you if it's hard to do on your calculator? To impress on you the idea that if you knew how to do it algebraically, it'd be quicker and easier. Okay. All right, here we go. 75 raised to the brackets 2x minus 3, end bracket. And then we also have 2.5 raised to, nope, 2.5 multiplied by 3 raised to the x. And I'm being honest with you here. Because I can't wrap my head around where these two are going to intersect, I'm going to go zoom standard. Just make sure I've entered it correctly. It looks okay. Zoom standard is zoom 6. So there's that one. The 75. And the reason why I was taking so long is it's crunching a lot of numbers to get that. And then there's the other one. Maybe they intersect way back here on the left-hand side of the screen, or maybe they intersect above. Let's try to just find the point of intersection, assuming they intersect above, up top. So if you go to your calculate menu and choose intersect, and put my cursor over here somewhere and go enter, 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 I get it. And for many years, I thought you had to see the point of intersection for it to work. You don't. The point of intersection has to have an x coordinate that's in your domain of the window. So they could intersect way up there at 18.8 as long as it's the x that's in your vision, in your domain, then you get the answer. So that means x is approximately 1.84. All right. Are we okay with those exponential equations? Again, once you learn how to solve things algebraically, I will admit that this is a difficult one to solve algebraically. There's a lot of steps. But it's a surefire thing, and you could be asked to do it on a written response. All right. We are going to go back now and look at that y equals a times b to the t over p. When you invest money, interest is usually, hopefully, compounded. And what that means is when I put the money in the account at some point later in time, so we're on the next page, right? At some point later in time, they calculate a certain percentage of my investment and they add it to my investment, right? So if I invest $1,000 and then they calculate maybe 2% interest, which is $20, my account will now have $1,020. You with me? The next time they calculate interest, they're going to find 2% of 1,020. So since you're finding a percentage of the amount that's currently there, your investment is continually being multiplied by some number, which means it's exponential. Okay? We need to become familiar with certain words like compounded monthly, compounded quarterly, compounded semi-annually, compounded annually. That's what this set of examples is going to teach us. I've explained that. So, this is nothing new. I've just copied the same thing from the previous lesson and put it here. We know all of this. Jerry invests $10,000 in an account, and the account is advertising that it pays interest at 8% per annum, compounded annually. Now, in the future, I will no longer need to tell you that that's what that means. When you see 8% / annum or 8% / A, it means an annual interest rate. The fact that it's compounded annually, everybody, means the period of time is 1 year. And I could use A for year, but I fear that that might confuse some people because we have an A up top there, which is something different. What does this mean? It means that Jerry on January 1st puts $10K in an account, and he keeps looking on his app, on his phone, at his balance throughout the year, and it's always going to say 10,000. He's celebrating New Year's Eve at 11 o'clock in the evening, and it says 10,000. He wakes up the next day, maybe late in the day, and he checks his account, and it will have 8% more in there. And then whatever that total will be, it will remain at that total for another year, and then it bumps up again. Bottom line is, this is 10,000. And I hope you see, I think it's worthwhile to say this, that when I started off today, I told you we did problems initially that were like this, right? And then I said, except that we had to take into account that maybe the y-intercept is not 1. Jerry's problem can be answered with this. Because p is 1. We don't need a p, right? So this is a problem you could have answered on the first day of classes. B, of course, is going to be 1.08, and I'll just give you a second to ponder where I got 1.08 from. 8% growth, right? 100% plus 8% is 108%. So the formula for Jerry's investment is y equals 10,000 times 1.08 raised to the t over 1, which is y equals 10,000 times 1.08 to the t. You don't have to write over 1. I'm just writing it twice. So how much money is in the account after 14 years? Well, all we're going to do is we're going to put 14 in for t. It's a straightforward calculation. $10,000 multiplied by 1.08 raised to the 14. $29,371.94. always rounding to the nearest hundredth, because that's what we do with money. Even though we don't tend to use physical money much anymore, that's what it is. How much interest is earned? Don't make this more complicated than it needs to be. He invested $10,000. How much interest was earned? $19,371.94. If I have 10,000 and then some point later in time I have that much, the interest is the difference. So the interest, not an interest rate, the interest is $19,371.94. By the way, you cannot get interest rates of 8% annually on most investments. When I was in high school, interest rates were as high as 24, 25, 26, 27, 28%. And I still remember this to this day that we were taught, if you can even put away 5% of your job earnings starting when you leave school, you'll be a multimillionaire by the time you hit 30, assuming you have a job. The problem with that logic is mortgage rates were also 27, 28, 29, 30%. And then the whole market crashed eventually. Any questions with Jerry's investment? The only way you're going to get true interest earned is if you invest outside. You can't get interest on a checking account. You know, it's pennies. You have to invest in dividends and stocks and all that other stuff. Okay, let's talk about Elaine. Elaine invests $10,000. She also has $10,000. She goes to a different bank, and the interest rate is 8% per annum. It's 8% per year. But that statement in and of itself does not mean it's compounded annually. It doesn't mean she's going to get 8% every year. It really doesn't. It's almost false advertising, but it's in her benefit. It's better for her. It's compounded quarterly. What does that mean? It means that if you visualize the year as being a block of time, and this is how I see a year in my head. I see a rectangle. I don't know what you guys think of. It gets smaller towards the end of the year. I'm alone on this? Okay. Weeks are slightly differently, and decades are even weirder. That's a year. You guys are now, I shouldn't have said that. Now you're trying to figure out what's going on in my head. This is a year. And this 8% per year means that she is going to get, well, she's not, but it means that this whole year is representative of 8%. But it's compounded quarterly, and what quarterly means is she's going to get interest 4 times a year. So if we visualize this as being cut into chunks of 4 quarters, what this means is she's going to get 2% in each quarter. That's what 8% per year compounded quarterly means. And if it were compounded monthly, and we took 8 divided by 12 and got, 0.6 repeating, if it were monthly, then she would get 0.6666% every month at the end of every month. And if it were semi-annually, she'd get 4% at the end of the first 6 months and the other 4% at the end of the second. And it turns out it's not going to translate to 8% because it's compounded, it's exponential. This 2% at the end of each quarter is going to give you more interest than it did in the last quarter. So her investment's going to be worth more than Jerry's. Now, what is A? A is still 10,000. What is B? B is now 1.02. So one way or another, you have to sort out how to go from that 8% per year compounded quarterly to 1.02. Right? Her investment here at this point in time is going to be multiplied by 1.02. And then at this point, it's going to be multiplied by 1.02. And here, it's going to be multiplied by 1.02. Now, what is P? P is the period of time you have to wait for that 2% to be added, right? So it's the length of time to get that interest. I want everybody to think about what you think P is. It's going to be a number, okay? Jerus, what would you say?
4.
It's not actually 4 because 1/4. Okay, 0.25. How many of you thought 0.25? Okay, if that's the case, we would put 0.25 here. And this is years, isn't it? So this whole thing from here to here is 1 year, which means this is 0.25 of a year. This is 0.25 of a year. This is 0.25 of a year. I just staggered them so you could see them, right? Did anybody feel as though P is a different number? Because there's another number that's correct as well. We'll come back to that. Okay. I would prefer years. So here is the equation for Elaine. Her investment is 10,000 A multiplied by 1.02 raised to the T over 0.25. If we want to find her investment after 14 years, we just need to put 14 into that equation. I'm not going to write that down. I will just show it up here. So I'm taking A times the base raised to T, which is 14, which is 14 divided by 0.25. We're okay with that? All right, so it's a little bit more. I'll give you a minute to write down the answer. I'm not going to write it down. The answer is her investment will have a value at the end of 14 years of $30,311.65. And the second part of the question is, how much interest will it have earned? Well, we just subtract the original investment. We get that much interest. Okay. Are we okay with the second part of this? All right, but here's a question. And I don't know, maybe nobody thought this, and I don't mean to, put thoughts in your head. I would go with this. But could you go with this? Could you say the period is 3 months? Well, I wouldn't write it down if we couldn't. It's not a trick question. Yes, you could. You could go with that. But then, if you did that, you would have to put the time in months. I would like you to figure out how many months 14 years is. 168? 168. And now what I want you to do, I don't want you to calculate this whole thing. Here was what we did to begin with, and we used 14. Correct? I would like you to take 14 divided by 0.25. 56? What does that mean? It means that the factor of 1.02 has been applied 56 times. I would like you to take 168 divided by 3. 56. So it's still applied the same number of times. And that's all that's important. I've said that from the beginning, that exponent is simply the number of times the application of the base has been applied. We have one more example here. How long will it take the two investments to reach 40,000? You cannot do this algebraically. You need to do it graphically. Okay. Is this what your example 5 is? Okay. So if I want to find out what Jerry's investment, the time is going to be, I'm going to put 40,000 in for Y1. I'm going to put 10000 times 1.08 raised to the x for Y2, and I want to find the point of intersection. We have already learned that after 14 years, Jerry's investment hasn't even reached 30,000. So to me, it would make sense that we want to look at maybe 25 years. This is just, I'm just throwing a dart in the dark. Okay? And clearly we have to go up to past 40,000 vertically. The scales do not matter, but I like to organize them a certain way. There's the ceiling that we have to reach. Here comes Jerry's investment. And part of you might be saying, I know how to do this, but there's a wrinkle to this question. I find the point of intersection, and I get 18.01. And I've engineered this question this way intentionally. What is the answer to the question? It's not 18 years. It's 19. Because the fact that that's more than 18 tells you that at 18 he has not reached 40,000 yet. Now, he will never actually have 40,000. But the question is worded in a way to imply that it's the time to reach 40,000. And if he doesn't have it at 18, I can even prove this to you. I can go trace 18, really close. But mathematically it's not there. We have to round up. So for Jerry, it's 19 years. And for Elaine, it's going to be less time because hers grows quicker. I would go with years. I wouldn't do the month thing. I think that looks okay. What is the answer to this question? This is Elaine's. Mark, do you know?
17 years and 7 months.
Can you repeat that?
17 years and 7 months.
No. Yeah, and it's good that you're rounding up. This 17.5 is 17 and 6 months, right? But she doesn't get interest every month. 17.75. Since she gets interest at 0.0s, 0.25s, 0.5s, 0.75s, we have to round up to the end of the next compounding period, just like we did with Jerry's, except we had to round up a full year. So for Elaine's, it's going to be 17.75 years. It's one of the rare cases where we have to take that into account. Now be aware though, on an exam it might just say the length of time required rounded to the nearest tenth. If you're given that instruction, you round to the nearest tenth.